Hey guys. So this is real-time predictive modeling with MLServer, MLFlow, and Apache Beam. So to give you guys a little bit of an agenda of what we're going to cover today, so a little bit about who we are, the problem we're trying to solve here, and then a quick overview of the architecture we've approached. Then we're kind of trying to dig into each little individual piece of that. We're going to talk a little bit about the training. We're going to talk about how we're deploying our models, and then we're going to talk about how we're scoring via Apache Beam. And then after that, we're going to talk a little bit about some of the things we've learned about it, the kind of like after V1 section, what we've kind of had to go back and adjust. So a little bit of background. My name's Devon. I'm a principal engineer at Oden. I'm one of Oden's first engineers, so I live with my mistakes. Oden's not a very big company. We haven't been around for that long, and I introduced us to Apache Beam and Dataflow, and I've had to live with all those mistakes this whole time. And I wrote my first Beam job in 2018, and this is now my 4th Beam Summit.
And hello everyone, my name is Jeswanth. I'm a senior ML engineer at Oden. I am not one of the Oden's first engineers, which means I have to live with all the mistakes or the bad engineering decisions that have been done before me. But yeah, I wrote my first Beam job in 2020, and this is my 3rd Beam Summit.
Yeah, I've dragged Jeswanth through all of my mistakes through the years. So who is Oden? So Oden's a company, you can kind of think of us similar to, say, New Relic or Datadog or one of these kind of like analytics platforms you're used to, but our customers are not developers, our customers are manufacturers, which are actually very similar to developers. They're people who care a lot about making things really well, and so they're really great customers. Most of them are in plastics, chemical, paper, a lot of like continuous process stuff. And it just means that we're dealing with a lot of time series data. And over the years, we've moved from being strictly kind of an analytics platform into an analytics platform with a layer of machine learning and AI on top of that. Roughly, this is how Oden uses Beam. So we use it in 2 ways. We use it for both streaming and batch. All of our data that comes in is read off of manufacturing lines that are on the factory floor. There's a PLC, programmable logic controller, that's hooked up to every manufacturing line. Famously, a device invented by Dick Morley, 1960s New Year's Day during a hangover, because he didn't want to do his work. And that little computer connects to a bunch of sensors on the manufacturing line, and then modern ones will actually communicate MQTT, or they'll work with some sort of locally hosted piece of software that'll communicate MQTT and push up into the cloud, to our services, to our endpoint, and we get that as pub/sub. Then we process that data in real time using Dataflow, so that's where the stream processing comes in. Lots of reading and writing back and forth to pub/sub from our Dataflow jobs, and we write that data out to primarily ClickHouse as our time series data store. We also dual write everything into BigQuery, and the way that we use Beam in a batch way is that we will actually deploy all of our streaming Beam jobs as batch jobs. This was, I think, the first Beam Summit talk that I gave, was how we do this kind of dual architecture. And to clarify, we are on GCP. So a lot of the stuff we're going to talk about in this talk is we focused around GCP services. This is a quick example of what we're doing. So this is our calculated metrics job. There's a classic example where you have 2 sensors that are measuring kind of the same thing. So in cable manufacturing, you're measuring the width of the cable and the height of the cable, and you actually just care about the average. And so we'll let the user define a function, which we'll define in JavaScript. So average diameter is diameter x plus diameter y divided by 2. And then we have a Beam job that's actually running a JavaScript interpreter inside of a p-transform, and in real time doing that streaming join and shipping that new metric, which is then just treated as a new metric downstream. So that's an example of one of these like real-time jobs that we have running right now. And this talk is actually about a kind of advanced version of that, which is called predictive metrics. So a lot of our manufacturers have what we consider these offline tests. So I manufacture a bunch of cable, and then I bring it to a side room, and I pull on it until it breaks, and I measure how hard I had to pull. Or I measure some paper, or I produce some paper, and I have to stretch it until it tears or fold it. We work with ink manufacturers, and we have to look at we do color spectrum testing. And some of these tests happen 40 minutes after the manufacturing of the batch. Sometimes they're 2 days after the manufacturing of the batch. So there's a really high value to being able to find out what these values are going to be or predict what these values are going to be based on the process conditions in advance. And so our hypothesis was that we could do inline measurement to predict offline quality and use Apache Beam to in real time, collect these metrics, build a rolling window of features, and then score them against a model and predict what that offline quality test is going to be.
Awesome. So with that in the mind, like the predictive metrics is our topic. Let's go over the high-level architecture overview of what are the different components that go into before we actually score against a model. So first, we engage with customers, and then data scientists do a bunch of experiments in defining what are the exact model that they want to use, what are the exact features, or do the feature engineering and all that stuff. And they develop a pipeline, and they can do that as a manual experimentation, or there is also an automated training that we support. Most of this is orchestrated via Airflow, and we deploy SKLearn pipelines, and automated training is done on Cloud Run jobs. And once we have the models, we log and track everything within MLFlow. First, there are two parts of MLFlow which we highly leverage. First is MLFlow experiments. It stores all the information about the model, all the training metadata, test statistics, pretty much all the deployment information that is necessary to ingest in the Beam pipelines later on. And after all the experiments are tracked, we do a peer review and then figure out which specific model we want to push into production, and we register that into MLFlow model registry. So this has been good for us. Like MLFlow is, I highly recommend if someone wants to keep track of their experiments and know or have model versioning. This is an example of how it looks for one single model. Like data scientists conduct multiple experiments. This is just an example of all the different experiments that they keep track of. They have metrics that they measure against, and all that stuff. And once we have the production models, there is a cron job which essentially syncs whatever models are tagged for production and deploys them onto MLServer. We'll talk a little bit about what MLServer is in this presentation. But essentially, all our production models are loaded into state within this, and then they're ready for any of the external services or any of the other clients to actually make inference calls. And the cron job also writes a cache to maintain what's the current version of the model that's tagged as production, so that all the downstream clients can actively know what specific, where to route the request to which version of the model. And next, how we train our models.
Yeah, so training our models, I'll talk a little bit about how we get this data. So as I said, in real time, we're taking these metrics and we're feeding them from the factory floor and pushing them through Dataflow, doing a bunch of transformation, ultimately ending up in ClickHouse as our time series data store. I think in the past, we've actually, if you came to previous talks years ago, we would talk about how we used to store it in Bigtable. We've since moved over to ClickHouse, and we kind of love it. It's a really good time series data store. We also manage a kind of customer-facing API for them to send us in batch a bunch of data which we don't get in real time. Things like these offline quality tests may come, an hour later, 2 days later, in these kind of like custom integrations. They'll come over these APIs, and that data tends to be stored in Postgres. No specific reason here. It's just the other database we have, and Postgres is great. We do run into a common issue, which is that we want to, and this is not specific to our training pipelines, but it's a specific problem we have across our entire analytics platform, which is that we want to have the join of these two sets of data. And so what we've actually built is an internal query language. We call it Oden Query Language, OQL. And there's a little bit of an example there in that slide. And that query language goes to a service which a query will come in from a data scientist who's trying to get a bunch of training data. The query will say, I want all these features and a bunch of labels so I can have my X and my Y. That'll come into the OQL query service. That will then break it up into two subqueries, one to ClickHouse, one to Postgres, and come back with the results and join it in memory and then deliver it back. In that process, when it comes back around to the Python client, it comes back as a pandas data frame. It's actually over gRPC, but then we turn it into a pandas data frame. We cache that locally using Feather, which I highly recommend everyone play with Feather. It's a great little way to store data frames. And you end up with it in the Python client. And that Python client could be on a data scientist's local laptop. It could be on a job that is running in production. To give you an idea of what it means to train a model, so the first step is data scientists have to perform some sort of EDA. They have to go out and understand the manufacturing process they're trying to model. I think Oden is unique in that being a data scientist at Oden, it's probably the only job where the role comes with a pair of steel-toed boots. We tend to send our data scientists on site to customers' factories to actually see the process in person. And I mean, once you've done one cable manufacturer, you have a good understanding of how to do other cable manufacturers. But especially when we get into these new processes, paper and ink are made in two very different ways, even though they're both continuous processes. Kind of like the first layer we have to worry about when we're building these pipelines is there's kind of a temporal shift you have to account for. If you have a manufacturing line that's moving at 10 feet per minute, and it is 10 feet long, then the thing you're measuring over here and the thing that you're measuring over here have a 1-minute offset in their data points. So we have to account for that kind of time-shifting behavior. The data scientists will then, put together a model and they'll experiment with it. They'll try a bunch of different iterations of it. And this is where MLFlow comes into play. They can log all of their experiments into MLFlow, and then we can also use this as a place to peer review among other data scientists or members of the data science team. And then optionally, we might train the model entirely locally. We might also train the model in the cloud. We might train that model on a schedule. So we also will use Airflow to kick off training jobs. Ultimately, these are run in Cloud Run. But yeah, we don't need very specific hardware for these models. We're not doing anything that requires like dedicated GPUs at least. But it's a nice way to have it regularly updating, which I know if anyone's built their own models, there's a lot to go along with the idea of regularly updating a model over a period of time that's in production.
Yeah, now that once the models are in MLFlow experiments, we register them into a MLFlow model registry, data scientists can play around with any kinds of how many ever number of experiments that they want. After peer review, the models are registered and their version, it's an example of how it looks in the production. So every time they decide to update a model, a new version gets created. And the deploy job, as I said before, it runs every hour. It ensures all the version models are from the model registry are deployed onto MLServer. And the production model version config, which is also cache, which we will use in the Beam job that we'll describe in this talk, consumes and sends inference requests to that specific model version. And this is an example of config. It's very critical to have to maintain the order of the metrics for inference. So if a model is trained on, say, the input metric, one as feature 1 and the next one as feature 2, it's essential that during streaming pipeline, we package the information in the same exact order for inference to be valid. So all that information is stored within here, and also the resolution of the data. This defines how much time-shifted features that we support in the real-time streaming scenarios. So as an example here, we can support up to 300 seconds of time-shifted features. And also, once we have that inference, we want to store that somewhere. All the metadata information on where we want to store that and how does all the IDs and how does it get into time series database, all that information stored in this config. And lastly, we load those models onto MLServer. And MLServer supports, it's built on top of Open Inference Protocol. So it supports gRPC and REST endpoints for clients to interact with. And also it gives us a nice abstraction from how do we package our data to actually send an inference request. That specific protocol is pretty standard for inference services. NVIDIA Triton and Ray, pretty much most of the inference services out there kind of use that.
Yeah, so the fun part for Beam is basically in scoring our model. So this is a simplified version of what this DAG looks like. If you actually look to the Beam DAG, it's not nearly this pretty, but I tried my best to make it something we could follow along. We read all of the metrics in from PubSub. we key the input metrics, so these are the metrics that are the features for our model. We key them by the the metric they're trying to predict, because we're modeling the prediction as just another metric, the way you would have like a stack driver metric or something. We partition them by their window, so different models have different window sizes. Some models you want a 5-minute window, some models you want a 3-minute window with different slides as well. And then we take those, once we've done that windowing, so we have these windows where it's like, here's all of the input metric values for this window pane, this period of time, for this particular predictive metric that we're going to be predicting. We then score the model. And then once we've done that, we've created this new metric, and we write it out to PubSub. Something that I think is kind of unique or interesting, I think I've seen other examples of this by other companies at actually the Beam Summit. We've wrapped our reader and our writer, like the inputs and outputs of all of our Beam jobs in a custom I/O connector it changes its behaviors based on which command line arguments you pass to it. I highly recommend everyone do this. It's a really, really useful feature. So basically, if you pass in the command line argument, this or the option to the job that says this is running in PubSub mode, where the input is this PubSub topic and the output is this PubSub topic, it will just run as a streaming job. But then if we decide we want to backfill a predictive metric, if we say we're done with this and we're happy with this model and we actually want to see what it would look like if we went all the way back to last year, then what we'll do is we'll deploy the job in a batch mode where the input is a BigQuery query, and we'll just pass in the query that's being executed as a command line argument. And we'll still have the output going to PubSub because we ultimately want it to go into our time series database. It'll just go to a special late metrics PubSub topic. Sometimes you want to write it back out to a file or something for deeper analysis, so there's different options for the writer as well. But yeah, very useful pattern. Highly recommend other people pick it up. For the partitioning by window part, this part's kind of interesting because you can't dynamically pick a window. You can't just, as you read the config, say, oh, actually, this predictive metric needs to be a 10-minute window. You have to know that in advance. So what we've done is we just have an argument we pass into the DAG or into the job that gets decided at the DAG build time, where here's the list of windows that you support. You support a 3-minute window with a 10-second slide, a 5-minute window with a 30-second slide, a 10-minute window with a 1-minute slide. And then what we do is, at the time of building the DAG, we just iterate in a for loop and build the DAG in that way to make sure we have one of those for each particular window. So yeah, not too hard, but definitely something that felt a little unintuitive at first. And then the last thing to kind of note here, I think is kind of interesting, is when we first started building Beam jobs, we did a lot of this reading a config in from the side. So for example, the calc metrics job, we had to know what metrics we were calculating. We had to know what the formula was. And what we used to do is we would do the thing that I think you'll sometimes see in blog posts talk about, where it's you run the sequence generator, and you have that go and fetch requests to some API to get back the config, and then you collapse that into a P collection view, and you load that into the P transform as a side input. And that totally works, but it actually just causes, for us, we found it caused more errors and more messiness than just reading the config directly within the transform. So basically, each one of our P transforms, or they're really duofens, they will go and fetch the request, or fetch the config from GCS, and then just, at the time it needs it, and then just cache it for some TTL. So basically, all of the duofens in this job that need to access this config, they all do the same thing, where they just, they say, let me get this from GCS, store it as a instance variable, and if it's gone more than 5 minutes, I'll get a fresh one. And this is how all the individual components work, and it works well for configs that are just moving kind of slowly, and I also just think it's easier for me to wrap my head around than the side input approach. So big fan of this approach.
Yep, a couple of things about model scoring here. So like Devon mentioned, for scoring, we send inference requests out to an external service. One of the interesting things why we chose MLServer here is it supports multi-model serving, which means we can share resources and deploy multiple models on one vCPU and save costs on that end. And also, we have evaluated, instead of using MLServer Vertex and deploy models there, it required us to package each model into its own container, which without any other customer. There was a deployment resource pool, which they started supporting when we started like looking into which options we have. But yeah, that would have cost us like vendor lock-in at that time. And yeah, also another important thing is, like I mentioned before, like the open inference protocol that comes from K-Serve's standard definition. It's like however MCP is going crazy these days with LLMs, it's kind of the thing that inference services kind of use out there. And the immediate thought that, next slide please. Yeah. And the immediate thought we would get is like, why should we even want to separate out the service? Like Beam inherently has run inference transform, why not just use that? So we also thought about that. The advantages that we get using run inference transform with embedded model scoring is we would cut down on latency as we don't have to send out calls to an external service there. And we can, like other talks are mentioning, use YAML configs and within the Beam pipelines and make our data scientists directly write the Beam pipelines for inference as well. And we also considered like using multi-language pipelines because most of our code is in Java Beam. We used to be on Python, and for reasons that we are not fully sure of, like as soon as we moved to Java Beam, we have an immense performance gain, so we never really wanted to move back to Python. So, but also we don't even have we don't have an expertise to manage like multi-language pipelines, and also that was just coming up when we did this work, so we never really opened that door up. But with the external model service, we can use all the pipelines that we have, all the composable pieces that we have already built in-house, and it's easy to test and scale the models, and we have availability SLOs monitoring and all other kinds of stuff that sends inference requests, which are not just Beam pipelines. So it opened us an avenue to expose inference not just for streaming cases, but for any of the batch cases, or if any other internal applications wanted to deploy their models, they could. We have like one unique place to manage all our ML inference services. And cons, we were skeptical about IO bound, but we'll see how it turned out towards the end of this presentation. And error tracking was difficult, but it's not undoable. We had to include our own retry logic and all that stuff, but it's not something that's unmanageable amount of work. So
yeah. Also, one thing I forgot to include, the one thing that's I think kind of fun about our jobs is they run for 2 to 3 months at a time, and we definitely did not want to have to tear them. Like I think there's some approaches that would require us to tear them down if you wanted, within the runtime inference. Yeah. So remote really paid off in that because we're deploying models much faster than that. Yeah, and so scoring against MLServer, I have today learned that there's the remote inference transform that's coming to the Java SDK. But for now, we have a lot of really ugly gRPC code. So yeah, we take the values, they come in that big window. We have to kind of organize them into rows, and then organize the rows into columns, and we build our two-dimensional tensor, which is just a 2D array, and we then build this really big, ugly gRPC request object, and we put it in this big, ugly try, except, retry loop. And it works pretty well. I mean, there was definitely a few edge cases we had to get through as we got there, but it's held up really, really well, better than I expected. So after V1, so there's a couple things that we've had to revisit since our first deployment of this infrastructure. So the first big one was we're on GCP, and we had to worry about streaming engine optimization. So we kind of took a big step back, and we looked at how much was it costing for us to run these models per line. So there's a model that's trained specifically for one manufacturing line, and what does it run us for that model to be running? And I think our estimate was something between $1,300 and $1,800 per year, which just wasn't a viable number for us. And when we looked at the spend on that, it was almost exclusively streaming engine. Because if you think about it, there's a ton of very small elements, little tiny payloads coming in, the individual metric values, and we're doing this big, very n-squared join on them. putting them all together over and over and over again throughout the day, and that's really where the streaming engine cost was coming from. So to solve this, we kind of added 2 steps into the process. The first was that we, did 2 approaches. One is we shrunk the serialized version of that metric that we were doing the join with as small as we possibly could get away with. And the second is that we broke the window into 2 stages to minimize the number of actual joins happening. So we added this new transform, shrink metric. We actually called it make metricita. Metricita is great. It is the diminutive form in Spanish. It's like my favorite thing in a language. But so we looked at the original metric class. There were these irrelevant UUIDs that were being stored in 36 character formats, so that's 36 bytes instead of being 120, instead of being 16 bytes for UUID. There was like a legacy name identifier. There was just a bunch of additional stuff in there, and we were serializing it using the schema coder. What we did instead was we introduced a new class that we would transform it into, which would just drop everything but the metric ID, the value, and the timestamp. And then also, we would use a custom coder to pack it as small as possible. And that really paid off. This is also, I love Corona-itas. It's the best like bachelor party joke, is everyone just drinks tiny beers. But yeah, so we created a new coder to bring it down to as small as possible, and we were actually able to bring the size from the schema coder, which is what we were using, from 138 bytes per metric down to 32 bytes, versus the serializable coder, which is like the default, which is 334 bytes. So I highly recommend everyone to look at how big if you're seeing big streaming engine costs, just look at how big every one of your payloads is when you serialize it down. The best way to do this, I find, is actually just write a Java test that executes the serializer, and you can like look at these values. So that was really nice optimization. The second thing we did was we then started looking at the additional, 38 bytes is nice, but when you actually look at the join, there's a bunch of other data that's being shoved in when that join happens. There's the join key itself, so the predictive metric ID plus a little bit of other metadata that I kind of breezed over. And then also there was a bunch of stuff about the window itself that took up a bunch of space. So that brought it up to something more like 338 bytes per. And so the next goal was basically, I can't reduce the size of the window, right? I can't reduce the size of the key very much. So the best thing for us to do is to reduce the number of joins that we're doing. And the best way to do that was to actually break it into 2 joins. So the first join is, you look at the greatest common denominator across all of the window slides, and you say, for us, that's 10 seconds. And so we say, okay, we're gonna take all the input metrics and bundle them into little chunks of 10 seconds of metric. And then we'll window all of those together. So this is roughly what that formula looked like before. This is my back of the envelope math of like what it was costing, what the function of streaming engine was, or streaming engine cost. It was a function of seconds in the day divided by window step size in seconds times the number of input metrics times the window size seconds times 384 bytes, which was the size of each element with all of its window and its key associated with it. And then the new formula looks like this. It's a little bit messier, but it breaks it into those 2 different join pieces. So there's the first join where we're bundling all of the input metrics into little 10-second chunks, and that's how many joins per day am I doing of that. And you can see it's using the original element size. And then the second one is when we're joining those chunks together, and you can see that a chunk of 10 of these values is only twice the size of an individual one of those values, and that's because the window is really big relative to the thing that we're joining. This is, I think, one of those things you just think about when you're joining really, really small data like we are. I don't think it matters nearly as much when you have big things that you're joining in your window in lower resolution. And that was really cool. We got a 95% discount, so it actually made the product way more feasible from a contract basis. And you can actually see the drop here, the first drop being from us switching to the Metricita class, and the second drop being from us reducing down to or breaking it up into those 2 separate joins. So again, highly recommend you spend some time looking at your streaming engine costs, at your streaming engine SKU, and also just looking at the bytes that are moving between stages and trying to back of the envelope this kind of math. It can make a huge difference.
Yeah, another tangent onto the cost saving here is like our use case at Oden for machine learning is like we have very tiny models, but we have a lot of them. So So resource sharing was very critical for us to actually scale our product. So with MLServer, we kind of hit we were able to get that. I've checked these numbers today before coming to the talk. So we have 4 CPU cores and 4 gigs of memory, and right now we have more than 150 production models. Most of these are SKLearn pipelines. They're very tiny, but we need to maintain a lot of them. And with every new customer that comes in, they add like close to anywhere 10 to 15 models. So, we served them, the latency was under 200 milliseconds, and there is a mistake on the slide, but it's like close to 350 requests per second is what the throughput is right now. This all sounds good, so we can celebrate our victory here. But there is a catch here. With resource sharing, we are restricted to one single Python runtime. We all know it's a dependency management in Python is kind of crazy. We have to do a lot of gymnastics. So all those challenges still existed in this domain. So whenever we want to make changes to our code to train new models or something, we always run into a bottleneck of maybe that breaks the previous models that we have. So we always had to be very extra careful in terms of monitoring what are the code changes, are we adding, are we deleting, and all that stuff. And also Python upgrade was like a crazy week for us at Oden. So when we had to do that, there was one specific thing. We upgraded from Python 3.9 to 3.12, and when we did that, Pandera had some backward compatibility issues, and we had to do a careful surgery, remove parts of the Pandera pieces in the pipeline, and then again attach back in the 3.12 environment, all that kinds of stuff. We still had a 26 minutes outage during then, so we had to do a postmortem. But yeah, shared resources is really good, but also we have to be careful about having only one single Python runtime for our models. So in conclusion, our takeaways are we had to pay close attention to our streaming engine costs on Dataflow to make our product scalable. But scoring the windows, forming the tensors and scoring, making all the transformations within Beam is like very efficient. If you think about it, it's close to, if it's a 5-minute window and say 50 features, it's close to like 15,000 data points. All of those processing is happening very seamlessly within Beam. And it's definitely worth testing your encoders. You might also get 90% or 95% discount on your costs. And syncing MLServer and Dataflow through a simple JSON config, even though it seems very naive, it actually worked very well for us. We haven't seen any issues with that. We implemented a 5-minute expiry logic there, so for us to always stay in sync with if a new config comes through from deploying a new model, at max we'll have 5 minutes delay in syncing that with the streaming system. And using external service was a good call. Now we have to go back and evaluate after Beam introduced model inference transform, but yeah. And I/O, as we were skeptical before, was never an issue. We didn't really had to go and dig into that for our performance gains. So maybe it's tomorrow's problem, we'll see. And also having this external service opened up an avenues for non-Beam inference capabilities. We are not restricted to only streaming cases right now, so we can also go back and provide that service to other applications. We are struggling to balance cost versus runtime, so a single inference server versus having a runtime saved us some money, but shared dependency problems always exist. And lastly, having this ecosystem of MLFlow, MLServer, and streaming via Beam made it easier for data scientists also to experiment and deploy models out there. There is always this gap between data scientists training a model and then getting that to production. Using this ecosystem kind of bridged that gap drastically for us.
Yeah, and so where are we going? So yeah, a lot of our models perform really well with like 95% correlation with a greater than 60% R squared value. Some offline quality tests are just harder to predict than others. This has been an interesting experience for us where, we are selling the idea of building a model, right? Like we have data scientists that work with our customers to get these models out in the field. And sometimes your inputs are just not indicative of the output you're trying to predict. And that's a really hard thing to plan around. That's like a fundamental hard machine learning data science customer relationship kind of thing. So there's been some good wins there, and there have been some misses, and it's hard to tell, is it like a modeling issue, or is it just a data issue at that point? You also run into inconsistency in the way that people are measuring things. You have lots of manufacturers who are measuring things with a physical caliper, and they're recording it into a pencil and paper spreadsheet, and everyone uses the caliper a little bit differently. So that's a challenge you have to kind of deal with. So there's a lot of inconsistency between manufacturing processes. There's also inconsistency between products. So we might train a model that performs really well on a particular product they're running for a period of time, and then they'll start running a new product on that line and it won't perform as well. And so that's new information we kind of need to encompass into our models, which is understanding which products being run on that line, and that introduces some complexity because that data comes from a different system, so it comes later, and that's going to be a whole thing for us to explore and kind of build out on. But yeah, we are also seeing success embedding these models, even simplified versions of these models that are a bit more directional, into bigger systems. So the screenshot here is of our operator assistant product. So it's a product that is on a screen next to the line operator, and it's showing them in real time kind of recommendations of how to adjust their process. And one of the inputs into this is us indicating whether or not the quality is going in a good or a bad direction based on previous examples. So that's pretty cool. And now that we built this infrastructure, we have a lot of opportunity to explore new models. So I think we were focused on this idea of predicting offline quality because there's a really clear business use case for it. But I think there's other interesting use cases in here. For example, manufacturing lines have this issue where there's a big time delay between two different parts of the line, where you're measuring something over here, you might be producing over here, and you don't measure it until a minute later down here. And a really consistent 1 minute lag with lots and lots and lots of samples, that's like a great thing for us to do a regression problem on to predict what that value is going to be. So maybe we can bring some of those values a little earlier in the pipeline using the same infrastructure. So it's exciting to kind of like keep building out with this, and especially since we've kind of like proven out that the infrastructure is so strong for this first use case. And yeah, I think that's all we've got.
Yep.